a bluish tint to it. But more so, if you go back and forth like this, even on a 6-inch wafer, if you had a gradient of greater than 1%, you'd actually be able to see a color shift. There's no color shift. That's what I'm looking for right now. So the uniformity on this is less than 1%. That's just coming from my experience. But if you were to measure this on an ellipsometer, you would see that it's very good. Now, by the nature of how
there is color change in this form. I mean, for example, in the corners, I can see any color change. I mean, I want to address the extent of uniformity claim for this, because I can see color change in this circuit, but not the entire circuit.
I don't see it. Plus, this wasn't a clean wafer anyway. Now, sometimes on the bottom side, you can see that. So, some of the ALD deposition works its way under, but not all of it. It's up to you if you want to put that back on, or
no, we don't do any experiments, so we have training, so we can use it again.
if you want. Now, if you were to run 800 cycles, that would be almost a purplish.
Now, so this is the result of 14 cycles.
400.
400 cycles? Because the last one is okay.
Just there is no balance.
What is your guess of the thickness?
There's legs on the bottom you can level it.
Okay, we can.
Yeah, there's on here.
Yeah.
This was just rolled on here, but you have posts underneath here. See? Oh, that's level.
Oh. Rather than the roll,
Yeah, because
we can put this on there. Okay.
yeah, this floor is not level.
Yeah. So that by that we can level it.
Yep.
Good.
So, do you have any rough estimate of thickness for this deposition after 400 cycles?
Yep. So really, really close to 336 angstroms.
300 angstrom is gonna be 30 nanometer, yes? 30 nanometer.
33.6 angstrom.
Yeah, so how long time, how much time it takes for 400 seconds?
Well,
Then
100 by 24 seconds.
Yeah.
Divided by something.
9,600 seconds or 96.
Divided by 60.
A little over 2
each
hours.
cycle,
Wow.
how long it takes?
But
25 seconds for each
about
cycle.
20,
about that.
25.
So depending on what thickness, you just add more cycles.
I understand.
So after we have the sample, and now you can just hit, let's do this. So PC pump, this is the PC pump recipe. This guy is. So it enables the pump, it turns it on, checks that it is on, makes sure the vacuum switch comes on, turns off the purge ISO valve, opens the roughing valve, it enables this phase. That's the statement that it puts in that black box. Then it waits 1 second, then it runs the gas recipe. So go ahead and hit PC pump. If you click recipe monitor. We're already, this is good pretty fast. Yep.
It's fine, right? That means
Question for
it is good.
start by centimeter. You have a question for start by centimeter.
Right?
That means
No,
it's
no,
coming down.
okay, okay, that's fine.
So go to vacuum. Right now, this did not reset that safety circuit. You'll see this quite often.
So we have to
Enable
reset it.
safety. Yep. And this will come there. With that was that abort we did yesterday. Tried to run the process and the safety wasn't reset, so it aborted it. So you just rerun the pump again.
Yeah.
Can you let us know how did you calculate the thickness based on number of cycles?
It's fairly well documented. Aluminum oxide at 300 degrees.
Oh, there
You
is
get
a chart.
0.84. It's a known value. Now, that's with aluminum oxide. There's a lot of
Depending on the
documentation.
material, I understand.
Yeah, some materials may not, you may not know that. You know, you
or
might have to,
not reliable, accurate, this, I mean,
yeah, but if,
correlation.
sometimes you just run some
No,
numbers,
it's positive. I just
and then
opened
you,
it. It's positive.
you measure the wafer
Yeah.
on an ellipsometer. This way you got an idea of what the native oxide is.
Yeah.
And then you run a material on it for some number of cycles, and then you do it on a ellipsometer, it'll give you thickness. You take that thickness divided by how many cycles, and that'll give you your growth per cycle. And therefore you can figure out what thickness you want. If you want thickness as far as material, and you want it fast, that's the better tool. If you want really, really good quality film,
Yeah, uniformity.
uniformity and pinhole free. That's for this country.
Well, no. I want to deposit a material like vanadium dioxide, so using a spiral. So I know that first I need to look for vanadium dioxide target from a company insert. For this one, if I want to deposit vanadium dioxide, so should I look for a TMA, so that is related to vanadium dioxide? What I should look for?
I don't think you can do any dioxide deposition in the ALD. You'll have to do that via RS cover. So that example, you couldn't do that. Now you could do aluminum oxide of both, but you can't do what you just said. So some
So we need to look for other process.
So imagine that I want to do either aluminum or steel or any other materials. What should we change? I'm not talking about the recipe.
It depends on if a precursor is available to do that. Because you have physical,
Here, you
Yeah.
change target. That's it.
yes,
What about here?
the chemistry.
Chemistry, exactly which component?
Whatever you're having for your precursor. That's what determines what you can deposit.
Exactly. This is what's called?
Ampule precursor. So precursor reactant are used.
Yeah. These are react materials. For
Yeah. Precursors are reactant, but you gotta react it with something else to
Exactly.
get something. That you don't have to react anything.
exactly. I
You
know,
already
because
have the
it's
material.
physical, it's not chemical.
Yeah, you're moving the material from one point to another.
Exactly.
This, you're creating a new material.
Creating okay.
Because it's a chemical reactor that
that's
to
why
create
you,
them.
you, okay, you are creating new materials
Yes.
as a result of chemical process.
Yes, because you
That's
have the
why it's
aluminum
not
part
like
here.
this changing the target or any, I understand, so you need, so this one, if this is the case, this one can cover a range of, so materials to be deposited on the substrate. Maybe,
It has its limitations.
So we
it
need
has
to,
limitation, I understand, definitely.
so we need to look for what kind of materials are deposited using ALD. There are specific categories or
Yes.
catalogs
Is that
which
right?
we can use as a precursor.
Yeah, there are some very common ones.
Yeah.
TMA, hafnium, zirconium. Okay, those are all very common
Yeah,
in
very
oxides.
So,
But it is open for any research.
There's different chemistry and different precursors coming out all the time.
New.
Yes. So depending on how well it's known or how well it's documented.
Yeah.
Aluminum oxide's been
Well done.
being done for like 70 years. So other stuff like cobalt, maybe not so much. And hafnium, doing hafnium, creating a hafnium oxide layer or a zirconium oxide layer. There's, different benefits to different ones. They're very similar, but some people, because of the properties, prefer one over another, depending on what they're doing for the process.
So when I put the PC vent,
This is a detector. Do you want to that? Are you sure? So you didn't hit it by
I don't
accident.
need. So
Well, if you want to continue, you hit resume.
no, I don't need. Close it.
Well, if you close it, then
Still.
that recipe will stay, it'll stay stuck there.
So
So in this case, you can't hit stop because you don't want to vent. So you can say, I don't want to vent, just stop.